Hey y'all, today I'm going to be talking about 6.1 slope fields. So slope fields are the other half of 6.1. And slope fields are going to kind of feel like calculus art. You're creating these pictures of slopes on a graph. And what a slope field really is the general slope of all of the possible solutions of a differential equation. So remember when we talked about with integrals, when we integrate, we get that constant integration c. And way back when we first defined integrals, we talked about how the general solution represents the family of solutions for this function. Well, a slope field is a visual representation of the family. A slope field is showing all of the possibilities of what this differential equation, what this integral could actually be as a function. So it shows all the places where the curve could go through the graph. And it kind of models out those slopes. So it really paints a picture of that curve. Okay, now that sounds really complicated, but their slope fields are actually really easy to make and really easy to interpret. They're just kind of a weird abstract idea. Okay, so we're going to make a slope field here with number one. We have dy over dx is equal to x plus 1. Okay, and you're not always going to get a table, but I'm going to give you the table to make it a little easier for you to kind of understand the process that we're doing. So all we do when we make a slope field is we plug the values in at each of these points into our differential equation. So for -1 comma -1, I'm going to plug in x and y into my differential equation. If you don't have x or you don't have y, then you just don't plug that number in. So at -1, -1, I'm going to just plug in the -1 for x. So dy over dx is equal to -1 plus 1, which equals 0. So my slope at -1 comma -1 is 0. Okay, just keep repeating the process. So at my next point, -1 comma 0, I do dy over dx is equal to still -1 plus 1 because x didn't change, so still 0. So my slope at -1 comma 0, still 0. Same thing for -1, 1, it would still be 0. I want to show you another one that's different though. So then as I get to 0, -1, now I have a different value for x. So dy over dx is equal to 0 plus 1. So my slope is 1. 0, 0 would still be 0 plus 1. So 1, 0, 1, still 0 plus 1. So 1, 1 comma -1. Now it is dy over dx is equal to 1 plus 1, which is equal to 2. So slope of 2, 1, 0, slope of 2, 1, 1, slope of 2. So notice, because I only have x in my differential equation, my slope didn't change if x doesn't change. So y changing does nothing to me. My slope only changes when my x changes. So now I'm going to take these slopes, and each of these represents a point on my coordinate plane. So at -1 comma -1, I'm going to draw a little mini slope of 0. So -1, -1 is here in quadrant 3, and a slope of 0, which I'm not going to use that. That's no fun. We're going to use our line tool, make nice straight lines. Slope of 0. Okay, so notice how I didn't draw a full complete line. I really just drew kind of a small line to occupy like a little bit of space around that point. That is the point -1, -1. And what I'm saying is that if a graph was to go through the point -1 comma -1, it would have a slope of 0 at -1 comma -1. Now, if I kept going at the point -1, 0, my slope is still 0. At the point -1, 1, my slope is still 0. Now at the point 0, -1, so down here on the y-axis, my slope is 1. So it doesn't have to be perfect. No one in the College Board is going to come out and measure your slopes, but it should generally look like a positive slope of 1. So pretty 45-degree angle is what you're going for. Through 0, 0, still a slope of 1. And through 0, 1, still a slope of 1. Now, 1 comma -1, slope of 2. So once again, still a positive slope, but it should look a little steeper than a slope of 1. And for all three of those points. So notice how I went from 0 to 1 to 2. So you can generally see on my graph that my slope is increasing just like it increased in the table. And if I wanted to keep finishing out this slope field, hopefully you kind of guess the pattern. As x increases by 1, my slope increases by 1. So this would be a slope of 3. This would be a slope of 4. So I could finish it out by just putting those slopes across. And of course, if I went the other way, my slope of 0 would then become a slope of -1. And then, of course, -2. And then if I wanted to put it on another line, remember, even though I'm going down in the y direction, that doesn't actually change my slopes at all. So as you can see, as we start to put more slopes on the graph, number one, they don't have to be perfect. I mean, if you compared my slope of 2 here to my slope of 2 here, don't even look like the same slope. They don't have to be perfect. You should just generally have the shape. If it makes you feel more comfortable, you can always back up your slope fields with some math. So I can be like, okay, your slopes look a little bad, but your slopes that you wrote over on the right side are good. So if you're ever worried about me thinking your slope field is looking a little off, just back it up with your math, and then you won't have anything to worry about. But it should generally kind of show the shape. Okay, so looking at this is a slope field. It is showing a field of possibilities for the function that if I was to integrate dy over dx, that I would actually get. Well, hopefully you can see this, but the function that this would actually create is a parabola. Just like so. Okay, so notice how my parabola kind of just followed the slopes in the slope field. So it represents all the possibilities. And just to kind of help back this up even further, if I was actually to separate, integrate, I'd get dy is equal to x plus 1 dx. Integrate both sides, we would get y is equal to x squared over 2 plus 2, not plus 2, plus x, and then plus c. So x squared over 2 plus x, we know that's a parabola. Plus c is representing that's the family of values. Depending on what initial condition, depending on what point I said your parabola has to go through, is going to change this up. So like, let's say I said your parabola had to go through the point -1, 0. Then you would plug in -1 and 0, and you'd get a specific value for c. And that value for c would make this into the particular solution for the graph that goes through that point 0, -1. That follows those slopes through the point 0, -1. Hopefully this is starting to make a little bit of sense. Okay, so slope fields are this field of slopes. It's drawing a picture of all the possibilities that the original function, this is f of x, could be. So depending on what point I tell my f of x to go through depends on what my value of c is going to be. So that's why c is the constant of integration. It represents the family of possible solutions. Okay, let's look at another one, another creating a slope field from scratch. And I'm not going to finish this one all the way out. We're just going to kind of do the middle. So this one has x and y. So dy over dx is equal to x plus y. So for every one of these, I'm going to be putting in both values. And obviously, the easier these differential equations are, y'all, you don't have to write all your math out because you can probably do it in your head. But I'm going to write these out just to keep everyone on the same page. So for -1, -1, dy over dx would equal -1 minus 1, which of course would be -2. So our slope would be -2. For -1, 0, we get -1 plus 0, which is equal to -1. For negative 1, 1, we get negative 1 plus 1, which gives us 0. Okay, so for each of these, I'm just adding these together. So 0 plus negative 1 is negative 1. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus negative 1 is 0. 1 plus 0 is 1. 1 plus 1 is 2. Nice and simple. Okay, now I'm going to take these. I'm going to transfer them onto my graph. So negative 1 and negative 1 is a slope of negative 2. So a little steeper negative slope. Negative 1, 0 is a slope of negative 1, so a little less steep negative slope. And 0, negative 1, 1 is slope of 0. Then 0, negative 1 is the slope of negative 1. 0, 0 is a slope of 0. And 0, 1 is a slope of 1. 1, negative 1 is a slope of 0. 1, 0 is a slope of 1. And 1, 1 is a slope of 2. And I said I wasn't going to finish it out, but I'm going to finish it out just for fun. So if I was to go all the way across this graph, and you, of course, can pause me and do this math to actually fill this out. So if you want to get practice filling out a slope field, pause me and fill out the rest of this doing the same math. But if you want to just watch, you can just watch. So if I were to go across, it actually follows this nice, cool diagonal pattern. So all my zeros, all my ones, all my slopes of 2, all my slopes of 3, all my slopes of 4, my slope of 5. And once you get to like a slope of 5, you're really just drawing a vertical line at that point. It's pretty much what it's going to look like. My slopes of negative 1, my slopes of negative 2, my slopes of negative 3, my slopes of negative 4, and my slopes of negative, that's a terrible negative 5. Slopes of negative 5. Like so. Okay. And unfortunately, because this one is dy over dx is equal to x plus y, I actually can't separate, integrate. This one just doesn't work out. So I can't show you what awesome function this actually is. It's a pretty weird one. It would probably be a rational function, which are a little bit odd. But same sort of idea. You just plug in those values of the slope and you get the value. So just to kind of check my math, let's look at this one down here. So I said this was a slope of negative 5. So this would be 1, 2, negative 3, 1, negative 2. So negative 3 plus negative 2 would be negative 5. So see, math backs up. So all you're doing for slope fields is you're plugging x and y at each of the points into my equation, into my differential equation. And whatever you get out for that slope, you're just graphing a small little line to represent that slope. Okay, so 1 and 3, which yes, weird that it's 1 and 3, but 1 and 3, those are your kind of, that's where you're usually going to see with the differential equation where you're actually graphing it or sketching it by hand. You're also going to see differential equations show up in a few different ways, a lot of it with matching them. So this first set of matching that we're going to talk about is we're going to match each slope field with the actual equation, not the differential equation, but the equation that the slope field could represent. So notice all of these down here are y equals equations. So all of these, you're not actually matching up the slopes, you're matching up the actual equation. So this is where your knowledge of graphs is going to be your best friend. So before we even start, I'm just going to come down here, I'm going to say what all of these graphs should look like. So y equals 1, that is a horizontal line that goes through the value of 1. That one's easy. Okay, y equals x. That's our parent function for a line. Nice and easy. Slope of 1. Y equals x squared. That is our parent function for a parabola. It's positive because it's positive x squared. Y equals 1/6 x cubed. That's not our parent function for a cubic, but it is a cubic function, so it's got that nice little x curved shape. Y equals 1 over x squared. So that is a rational function. but specifically because it is a difference of 2 between the power on the top and the power on the bottom, which you might not know that rule by heart. But so top is x to the 0, which is 1. Bottom is x squared. So because 0 and 2 is a difference of 2, both of the portions of the rational function go up or down towards the same direction. It's positive, so it goes up. Fun little fact, if you didn't know that, you can always use your Desmos calculator to help back that up. Sine of x is that sine curve, so it creates the S shape. Cosine of x is the cosine curve, so it creates that C shape. And then natural log of x, this is probably one you don't know by heart, but is that upside down exponential function with a little asymptote of the vertical variety on the side. Okay, so these are what these functions look like. So now you're taking each of these slope fields and you're matching up to the function, that shape it represents. So that A, so we notice on A, we're kind of swooping up and swooping up. Which one does A look like? Well, A looks just like 11. So we'll match A to number 11. So looking at B, it goes down and up and down and up, kind of like that oscillation. Okay, so if we follow it, looks like that. Okay. Sometimes it can be hard with these to know which one is cosine and which one was sine, which hopefully as I started to do that, you're like, okay, well, that's either cosine or sine. But remember, cosine is the one that hits that slope because of that C shape at the x-axis. So cosine of 0 is equal to 0. So it hits that slope at the x-axis. So B is, in fact, cosine. Then part C, this one looks just kind of like a shifted over version of our question number 1. So this one is our parabola shape, swooping down like that. So C goes with our parabola. Number 9. D, super flat line, shoots straight through. I know it represents all the possibilities, but really we know it's y equals 1. Okay. So D would, of course, be 7. E, same sort of shape to B, but notice how this one now creates that S curve. So it swoops through. It's actually curving through there instead of being 0. So it is our sine curve, number 12. And then F. So notice it almost looks like E. It almost looks like that sine, or looks like B. It looks like that cosine. But as we get out towards the edges, it's super steep because just like our cubic function, it would shoot up and then up and up like that. It kind of sleeks out as it goes out to the edges. So it is that cubic function, number 10. Then I'm going to skip G because G is hard, but H, hopefully you can see, it's that y equals x, that line straight through the middle. And then last but not least, G. So G, notice that it does actually have that curvature to it, and you can't see it because these are little pictures of TI-84. So on your TI-84, you wouldn't be able to see it either. Your TI-84 actually can create slope fields, but there's actually perfectly vertical lines there through the axis, or just no line, because what is a perfectly vertical slope? Well, it's an undefined slope. It's an infinite slope. So we don't actually have a slope there. So that is representing our asymptote. Okay. Now you might be wondering, well, Mr. Arbone, why is there that flip side on the other side? Well, remember, this is representing the family of functions. Y is equal to absolute value of natural log of x. So technically we could flip that over to the other side, and it could also be the same function. Okay. So 14, last but not least, is G. Now, these ones can be really easy if you know the shape of the graph. But if you know the shape, if you don't know the shape of your graphs by heart, these can be kind of hard, especially because you probably wouldn't have a calculator for this section. So the next type of matching, I actually like more because you can do a little more calculus to check it out. And you could, if you wanted to, you could derive these, get differential equations, and then plug in values to back up slopes. But that's a lot of extra work. So I really like these. If you know the graph, just go by matching the graph. Ones like this, we're matching the slope field with the differential equation. So what we're doing instead, this time we don't have the original function. It's really too much work to try and separate, integrate all these to get the original function. So instead, I'm just going to plug values in and match up those slopes. So the first one I always plug in, because it's the easiest number to check right off the bat, is to plug in 0, 0. Because if you plug in 0, 0, it can really easily start knocking stuff out. So for number 15, I'm going to plug in 0, 0. So dy over dx, 0, 0, that would give me 1/2 times 0 plus 1, which would give me a slope of 1. So how many of these graphs have a positive slope of 1 through the origin? Well, not A, not C, not D, B. It's the only one that has that positive slope of 1 straight through the origin. So right off the bat, which one do I know is B? Has to be 15. Nice and easy. Okay, let's look at 16. So 16, I'm going to plug in 0, 0. Okay, all I have is y, so 0, 0 would just give me 0. So let's look here. Okay, D, I can't see a slope at all, so I don't know. C, it looks like it would follow the diagonal pattern, so I probably have a slope of 0 right here for C. So C is definitely a contender. A, hard to say because there's a 0 pattern here as well. Okay. And like I said, we don't know about D either. It could totally be 0 in the middle. But what I want you to notice is that the next one up on all 3 of these is different. So plugging in one more point is going to help me eliminate between any of the 3 of these. So that's the nice thing about starting with 0, 0, is then you can pick one other point and then you can start to differentiate slopes. So let's plug in, that is 0, 1. So I'm going to plug in 0, 1, which is just y. So it would give me just 1. So which one of these has a slope of positive 1? That would be D. So 16 would be D. Okay, so I already plugged in 0, 0. So for 17, I'm not going to bother with plugging in 0, 0. I'm just going to plug in that 0, 1. So plugging in 0, 1 to 17, that would give us 0 minus 1, which would give us negative 1. So which one of these between A and C has a slope of negative 1? That would, of course, be C, that negative slope of 1. So 17 is knocked down to C. And then last but not least, 18, I only have one left, so it's probably A. But let's do some math just to check. So I am going to plug in that 0, 1. So that would give us negative 0 over 1, which would, of course, be negative 0, which you might have seen negative 0 this last week because it was so cold. But we know negative 0 is really just 0. So which one of these has 0? Well, it is, of course, A right there as it repeats that 0 up. And so 18 would be A. So I like these ones a little bit better when you're matching a differential equation with the slope field because you don't have to know or be able to picture the graph. You can just plug numbers in and match those slopes up. So for matching the differential equation to the slope field, plug the numbers in and match those slopes to the pictures. For your matching the equation, if you need to, you can derive these and get the differential equations to plug in numbers. But if you can picture the graph, then you can just match the graph to the slope field. So let's look at one last little bit. At number 19, this is actually a super old FRQ, but it is a free response question. So I want you to kind of get the idea. of what you could kind of have to do for slope fields on differential equations. You do actually have FRQs where you'll sketch a slope field. That will be a whole point of it. Could be 2 to 3 points depending on the slope field. Or you could get them like these where we're sketching solution curves. So for number 19, the calculator drawn slope field for dy over dx equals xy, x times y, is shown in the figure below. So this is our slope field. The solution curve passing through the point 0, 1 is also shown. So notice they did the same thing I've been doing. They already drew you the solution through the point 0, 1. So they want us to sketch the solution curve through the point 0, 2. And I'm going to sketch that curve in green. So 0, 2 would be this point right here. So I'm just following the slopes. So whoop, like that. That's a point on the AP exam. Man, that's an awesome FRQ. Okay, so solution curve means to just make sure your curve goes through the points and then just follow the slopes. It does not have to be perfect. They're not expecting you to an artiste. This is a sketch. Keep that in mind, but it should pretty closely follow the slopes. So second question, we want to sketch a solution curve through the point 0, 1. So 0, 1, smack dab a point, follow those slopes, just like so. And we're in business. Nice and easy. Okay, that's it. So y'all, that is slope fields. That's pretty much the only way you're going to see them. You'll see them lots of different graphs. You'll have to graph them by hand. You'll have to match graph the differential equations. But basically, anytime you see those pictures of slopes, that's a slope field. If you got any questions, comments, and concerns, of course, reach out to me. But otherwise, start working on your practice.